For our expression tree data structure, we will now implement a destructor so that we can release the memory of the complete expression tree. We will also implement some methods so that we can print the tree structure, and some method for, of course, evaluating the value of the complete expression tree so that we again have a calculator that computes a value from what the user wants to compute. You will see that all these implementations of these functions have something in common, that you will visit in these functions each expression node exactly once. This is called traversing the expression tree, and that we will apply some kind of operation to each node. For the destructor, for example, this would be releasing the memory of a certain node. You will see that the implementations are always kind of similar, but there are certain differences. We will first develop for each of this method the algorithm just by considering this concrete example, and then afterwards we can see what they have in common and what are the differences and how can this be formalized. Our destructor for the expression tree gets called with a pointer to the root node of the expression tree. And if this is a binary or unary expression node, then we first have to release the memory for the child nodes before we can release the memory of this node itself. And for the child nodes, of course, we have the same rules. If they have sub-child nodes, then we have to release the memory for them before we can release the memory for a child node. And of course, this can be done recursively. And the idea will be the following, that we call first the destructor for the left child node, if we have a binary expression node. And after that, we will call the destructor for the right child node. And then we release the memory for the node itself. So this is now just for the case of a binary expression tree. But of course, this can be generalized for our case where we also have unary expression nodes. So in this case, we would have the following. We would first call the destructor for the left child node. This again would call the destructor for its left child node. And here we actually begin the first time to release actually memory for a node. And after that, this call returns. Then we release the memory for this right child node and so on. And then after all these child nodes and their sub-child nodes were released, we release the root node last. And this, of course, easily can be implemented. So first we have to check that expression is not a null pointer, that it's a valid pointer. And then we also have to check that expression kind is a valid value for an expression kind. So the typical pattern for checking that. And now we have to distinguish between the cases that we have a binary expression node or a unary expression node. In this case, we have to do this recursive course of the destructor for the child nodes or the only child node. And for distinguishing these cases, we again use this typical pattern. Let me copy this for the case that we have a unary expression node. And I just change this here to unary and also the end marker to the unary end marker. And then we have this two calls of delete expression. And this first gets the pointer to the left child node. And then another call with the pointer to the right child node. And this will give us, by the way, a warning from the compiler because delete expression expects a non-const pointer. So let me also do this for the unary expressions, but we will deal with these warnings later. Now, here we can actually release the memory of this node, and maybe we also insert some printf so that we actually see how many times a node was released, how many times the destructor was called. It should be called for every node once, exactly once. So now first you will see all these warnings, but no error message. So we can run this executable, and then you can count how many times you see calling free, and it should match the number of nodes that we have. Now to get rid of these warnings, we simply do a typecast, and let's talk about design issues related to that afterwards. So we just cast away the constants from this pointer. And with that, we should get rid of these warnings. Okay, that's it. Like in the last C programming workout, we will first print out the tree structure of an expression in some textual form. And you will see then afterwards, with some minor modification, we can generate some LaTeX code from this printout, which then can be visualized nicer in some graphical form. For printing out the expression tree, we will use this algorithm, which is very similar to the algorithm of the destructor. We also visit every node of the tree exactly once, and we also apply some operation to a node. Instead of releasing the memory of a node, we will print out a representation of the node. If it's a primary expression node, then we print out the stored value. If it's a unary or binary expression node, then we print out the operation that it's representing, a symbol for this operation. And the major difference compared to this algorithm for the destructor is that we first apply this operation and then we visit the child nodes if we have a binary or unary expression node. So this is the major difference. The minor difference is that we have this additional parameter for an indent. We initially will call this function with the root node and the indent of 1. And for every subchild, this indent will be incremented by 1. That means initially we will, in this example, print the root node with an indent of 0. Then we print out its left child node with an indent of 1. This will print out its child nodes with an indent of 2. So after that, we would have printed out the complete left subtree of the root node. And then we would print out the right child of the root node with an indent of 1. And this would then again call recursively this function to print out its child nodes. So this is basically the idea. Now for the user of our data structure, we of course want to provide just a simple call for printing out an expression tree where you do not have to pass an indent. So we will have a public expression tree function which just takes a pointer to the root node, and we will have an internal function for printing an expression tree which actually has this indent. And our public function just calls this internal function initially with the root node and indent 0, and then in this internal function or this recursive function calls actually happen. So let's begin with the function call in the test program. Basically similar to the destructor. And then we have to declare this function first. So I will place after this comment all the methods that will be declared. So this print expression tree function gets a const pointer to the root node of this tree. Now let's copy this and use it for the source file. So here I also used this comment to mark the section for the methods. And then I turn this declaration into a function definition. And then I also need this internal functions. One function for printing the indent, and I simply will use for now a loop. Later I can show you how printf can be used for doing this a bit simpler. So this also means that I have to include standard def for size d, but I have to include this anyway. So let's do this now, and then we can go back. So The next function is for printing the expression node itself. So this gets a pointer to the expression node, and then I also need an internal print expression tree function, which also gets an indent. And this just has the same name as this external print expression tree function, just this additional underscore. We can call this internal print expression tree function with indent 0. And then we can begin with the implementation of this internal print expression tree function. Here we first check whether expression is a valid pointer, and after that whether expression kind is a valid value, using again the usual pattern, of course. Okay, and then we have to check whether we have a binary expression. Also the usual pattern, checking whether it's in this group of binary enum constants. And in this case, we first print the representation of the node itself with the current indent. And then we do a recursive call for this print expression tree function with a incremented indent. For the left node first with indent +1, the right node also with indent +1. And then I can use this here for checking the next case, that we have a unary expression node. So I just changed this again from binary to unary, also here. And in this case, I also first print the expression node representation, and after that I do a recursive function call with, in this case, a pointer to the only child node. And then in the last case, I simply print the expression node representation of the primary expression. And because of the assertion above, nothing else is possible except these three cases. Now here in the implementation for printing the expression node, we first check again whether the pointer is valid. We will actually need here a parameter for the indent. We will not check here with an assertion whether the expression is having a valid kind. This will happen afterwards, as you will see. So first we print the indent, and after that we check whether we have a binary or unary expression. In both cases we simply can print a representation for the operation represented by this expression node. So here the end marker for the unary group is used, and the begin marker for the binary group. And then of course we can use a switch statement for the expression kind, and then we have to go through all the cases where we do not have a primary expression kind. If we have a operation for adding two expressions, a plus followed by a new line, and the same I will do for all these other enum constants, except for this one and primary expression kind that we currently have. So this just takes some effort. And we also have the division and Then we also will use a default, and this will be the only case that we do not return directly from this function. For the primary expressions, currently we just have one case for that, so I can simply use one if for that. And in this case, I simply print the value of the node. For that, I need this macro for printing a unsigned integer with 64 bits. That means I also have to include this header file int types. But let's do this later. So uint here, and then I return. So if we haven't returned, we will reach this point, and in this case we have an internal error. That means we forgot to check all cases for possible enum constants, and then we print the error message and exit with exit code 1. And maybe we also should print what expression kind was not handled above. Okay, now we also have to include int types. Okay, and that should be it now. Actually, we should now be able to compile this. Okay, that's just a typo. Okay, but now it should be possible. Yeah. Now let's test this. And oh, actually we get an internal error. The expression kind 5 was not handled. So let's check the header file and let's do some counting. So 0, 1, 2, 3, 4. So 5 is the end marker, and also the value of the first enum constant in this unary group. And of course we forgot both of this unary kinds. So I just add here a case for minus and for add. And now all cases should be handled. Yeah, okay. But maybe actually it would have been a better idea to handle these cases separately, so that we can see from the printout whether it's a unary plus or binary plus, and also for the unary minus, something like plus unary. Then it's maybe better readable, as long as we do not have this graphical representation. Okay, maybe that's clearer now, or more expressive. So, yeah. So let's begin with the declaration of this eval expression function. It also gets a const pointer to the expression root node, and with that we now can, in the section for methods, begin with the implementation, and this will basically be the same as for this print expression tree. So we also first check that we have a valid pointer with an assert, and that we have a valid expression kind. And then we first check whether we have a binary or unary expression. So we use the begin marker for the binary group and the end marker for the unary group. And then in here we have to handle all cases with a switch statement. So, and the pattern will be for the binaries always the same. You evaluate the left node and the right node, and then you use some operator depending on what the expression node represents for computing the value of the current node. Okay, let's align that, and then I can basically copy this and change it to a subtraction. And then you see the pattern. This now has to be repeated for all kind of operators, including the unary operators. So also division. And for the power operator we actually have to do a function call. That means we also have to include math.h. So let's do that so that we do not forget it. And then we still have to do this unary operators. At least the unary minus is doing something useful. And for the unary plus we actually do not have to do any computation. We simply return the result from eval for the child node. And then we also need a default so that we can later handle errors. If we do not return, it should be an internal error. But first we have to also consider the case that the value is actually just stored in the node. Then we simply return the stored value. So that means we simply return expression literal uint. And if we reach this point, we have an internal error. And then we also should print the expression kind that wasn't handled. You saw that this can be useful. And after this error message, we also should exit with exit code 1. And then we also have to actually call this function in the test program. Usually I first change the test program before I begin with the declaration and the implementation. Okay, but that's how it goes. Okay, and now we can test it. You see, I forgot to include standard I/O. And this wouldn't have happened if I first have written the test program or modified the test program, tried to compile it, see whether I just have linker errors. So in this case it was not a big deal, but in general at this point you don't want to have problems. So let's also get rid of this debug output so that we have it easier to modify the program so that we can generate some LaTeX code. For generating some LaTeX code that we then can translate into some nice pictures, some PDF or PNGs, we just have to make some minor modifications. We have to generate some brackets around these nodes in our printout so that each node and its subnode is surrounded by brackets, and then some additional LaTeX before and after this, some prologue and epilogue. For example, with this LaTeX code, you could generate this picture, and if you want to have circles, then feel free to use some ticks magic. And of course, I, for example, also would like to see the value of the expression node. So with LaTeX, we have lots of options. So basically, we just have to print a open bracket before each symbol for identifying an expression node, the kind of expression node. And for this head, we also need the code in LaTeX for printing this head symbol. And you have to use these 2 backslashes for printing a backslash. And we do not need this unary. This will be visible from the graph. And with that, we're already closer now. We also should use brackets for this value, one before the value. So this has to be before the % sign, and one after the value. Maybe in the same line, before the new line. And with that, we already should be closer to what we want in the LaTeX code. Now we also need these close brackets for each expression node, and to make it nice, this close bracket also should be coming after indent, the same indent that was used above for the expression node itself. And then we of course also need this for unary expression nodes. So I just copy that, and that's it. So that's the next step. Now let's see. So what I need now is some prologue, this including of packages and stuff like that, and then a epilogue. So it begins with document class, and then this preview and the margin, and this should be standalone. And then all this other stuff, including this ASM math and so on, and the forest package, of course. And then we need this begin document, and then also begin forest before the tree. So this end document comes after printing the tree, but let's first print this begin forest and end forest. And I just move this up here. And then I also want to print the value. So this needs to be in some math environment, and it's also kind of centered. And yeah, maybe also first some text value, and after that the numerical value. And of course we just get that by calling eval expression. Okay, now let's see. Okay, looks kind of good. So now we should of course remove this printf for this eval expression. We now have this in the LaTeX code, and then we can redirect this into a file. So, and then we can try to compile that with Lua LaTeX and open the PDF. So almost, the package name was wrong, the document class was wrong, but let's try again. Yeah, almost. Expression tree also should be centered, but that's easy to fix. We just put a begin center and end center around this forest, and then both should be centered, not just the value of the expression tree. Okay, and that's it. So the next step, of course, will be to integrate this data structure for expressions into the parser so that the parse functions generate nodes for the expression tree, and in the end we get back from the parser a pointer to the root node of an expression tree. And this will be the next step also for the compiler project, that we have some data structure that we get back from the parser that then can be used for code generation.